What's that? It's absinthe.
Known for its alleged hallucinogenic effects, absinthe is one of the most infamous alcoholic beverages. It was banned in the U.S. in the early 1900s, but recently reintroduced in 2007 due to studies proving that its effects were not nearly as severe as what people had previously believed.
Say, I'm not feeling anything.
Me neither. Sober as a judge.
How about you?
I'm not feeling a goddamn thing. It's absinthe and bull.
However, if you speak to someone who has consumed absinthe, they will likely tell you that it is, in fact, a lot stronger than a normal alcoholic beverage. The molecule responsible for making absinthe different from other types of alcohols is alpha-thujone. Alpha-thujone is a convulsant that can cause muscle contractions and unwanted neural activity. However, despite all of these negative effects, the body is still quite resilient to it. So, for our Molmodac project, we wanted to know how the body deals with alpha-thujone and manages to get us from here back to here.
Alpha-thujone is metabolized by the protein cytochrome P450, shown here in green. In order for the metabolism of alpha-thujone to begin, human cytochrome P450 must be present and carrying a hemoglobin group in its active site, seen here in the cartoon representation of the protein. P450 is a monomeric oxidoreductase that catalyzes the transfer of electrons from one molecule to another. The important iron-containing hemoglobin group is stabilized by hydrogen bonding with nearby amino acid residues such as arginine, cysteine, and tryptophan. However, it is the iron of the hemoglobin that interacts with alpha-thujone and initiates the free radical mechanism that leads to metabolism. But first, iron must prepare itself for reaction. In the first step of this preparation, water dissociates from iron 3. Next, NADPH acts as a reducing agent, donating a hydride. This reacts with molecular oxygen and iron to create the ferric hydroperoxo complex. The iron is oxidized back to iron 3 and donates those electrons somewhere else in the protein. The exact location of the donated electrons is not entirely known and has not yet been elucidated by the literature. The ferric hydroperoxo complex then abstracts a hydrogen atom from a water molecule, simply shown in box 4 as H+, from a water that is being held by hydrogen bonding interactions with threonine 309. Then, in an E-beta-like step, iron forms a pi bond with oxygen and the newly formed water is eliminated. This step oxidizes iron to iron 5, which is incredibly unstable, so much so that it has the ability to abstract an electron from a nearby molecule. There are two sources of this electron, the heme group or the P450 protein itself. Either way, a radical cation is created on a nearby atom.
In this slide, we can see the first modification to alpha-thujone in the catalytic cycle. The hydrogen at the 4 position of alpha-thujone is abstracted onto oxygen by a homolytic break of the pi bond between the unstable ferryl species and oxygen. This regenerates the more stable ferric iron oxidation state, which is now bound to the equivalent of a hydroxy radical, and ultimately eliminates the radical cation. This also generates a radical at the 4 position of alpha-thujone because of the homolytic break between the abstracted hydrogen and carbon at that position. We will see what happens as the mechanism moves forward, but in the meantime, let's consider the unique nature of the alpha-thujone radical intermediate that we just generated. This slide shows the several intermediates and products which result from the radical that is generated at the 4 position of alpha-thujone. Even though the intermediate is essentially planar, for the most part the alpha configuration is retained, and 4-hydroxy-alpha-thujone, which is seen labeled 3-alpha at the bottom left, is formed. This is due to steric interactions at the active site that favor the rebound of the hydroxy group back onto the face from which the hydrogen was abstracted to begin with. Essentially, the molecule is constrained and rotating to expose the opposite face, where the rebound of the hydroxy group forms 4-hydroxy-beta-thujone, seen labeled 3-beta at the bottom right. A cyclohexene radical intermediate can also be formed by a homolytic ring opening between the bond between the 1 and 5 carbons. This rearrangement of the radical is an example of the behavior of a radical clock. Radical clocks are very useful to chemists. They are able to measure the rate constant of the unimolecular radical rearrangement, seeing here the formation of the cyclohexene. Then, with the ratio of both the rearranged and unrearranged products seen along the bottom of this slide, the rate constant of the formation of the unrearranged products can be extrapolated.
The radical then attacks the iron-oxygen bond, causing homolytic cleavage. Homolytic cleavage entails the breaking of a single bond in which one electron remains on each of the atoms. This further reduces the iron and to create a new carbon hydroxy bond product. The formation of 7-hydroxy-alpha-thujone is very similar to the mechanism forming 4-hydroxy-alpha-thujone. The mechanism begins with the same homolytic cleavage of the iron-oxygen and carbon-hydrogen bonds. The radical attacks the iron-oxygen bond, causing a new carbon-hydroxy bond to form, and the iron becomes reduced. This leads to the final 7-hydroxy-alpha-thujone product. As you can tell from the boys in Eurotrip, absinthe does pack a wild punch, but by understanding the mechanistic pathways and protein metabolism of this molecule, it will help to create a better awareness of our body and how it deals with the ingestion of this beverage.